Alright, welcome to lecture 8, and this lecture we're going to talk about recursion, and I have my fancy recursion hat on because it's Christmas Eve, so Merry Christmas Eve to those of you who celebrate Christmas. So recursion, this is the big one. This is what CSE 222 is really all about. This is the concept that kind of makes or breaks computer science for a lot of people, and so we're going to go through this in very careful detail to make sure that this really makes it for everyone. This is a subject that hopefully you've already encountered in CSE 215, discrete structures. Either you've taken that course previously or you're taking it this quarter at the same time as 222, and everything we've done with inductive reasoning, mathematical induction, the idea of a base case and a inductive step, that ties into recursion. And as we continue developing that, if you're taking discrete structures this quarter, those concepts will start to harmonize with what we're doing in data structures with this idea. The concept is very simple. Sometimes it's easiest to describe something in terms of itself. And that can feel like kind of a quirky thing to do, but let me give you a very simple example. We can write, a mathematical function, sum n, and write this as the sum from I equals 1 to n of I, which is 1 plus 2 plus 3 plus ... plus n minus 1 plus n. And so we can write this function sum of n, which takes an integer, and we're assuming, n is bigger than or equal to 1, so only positive numbers. And it tells us the sum of the first n integers. And so, for example, sum of 3 is 1 plus 2 plus 3, which is 6. Sum of 2 is just 1 plus 2, which is 3. Sum of 1 is just 1. It's 1, added with nothing else. Sum of 100 is 5,050. A very famous anecdote about a math student in grade school who the teacher asked the class to add up the numbers from 1 to 100 because he wanted the students to be quiet for a while. And the student came back almost immediately and said, "I have the answer," and that was the answer. And he used a different way of adding. So that's a good summation to know. So we can do this on pencil and paper by just adding a bunch of numbers together. If we want to get a computer to do this calculation for us, we know we can use a for loop. These summation symbols, they're always translatable to for loops. For I equals 1 to n, and we could initialize sum to 0, and in our for loop we could say sum equals sum plus I. And when we're done, we would have, the sum of the first n integers. So that's not hard to do, right? We can do that in a C program. It's a few lines of code. But I want to think about a different way of describing what this function does. So we know that if we add up the numbers from I equals 1 to n, that's the same as adding the numbers from 1 to n minus 1 and then adding this extra number on the end. In other words, 1 plus 2 plus 3 plus ... plus n minus 1 plus n. This is the same thing as this plus n. I've just added some brackets and some space here, right? But this is clearly the same as this. But this thing in brackets, this is sum n minus 1. In other words, this is the sum of the first n minus 1 integers. And so we see a relationship here. The sum of the first n integers is the sum of the first n minus 1 integers plus good old n. Or if you want to look at this in a particular case, 1 plus 2 plus 3 plus 4 plus 5 plus 6, well, that's just 1 plus 2 plus 3 plus 4 plus 5 plus 6. But what this means is if we had a way to add up the first 5 integers, we could easily figure out the sum of the first 6 integers. Just take the sum of the first 5 and add 6. And if we had a way to calculate the sum of the first 9 integers, we could calculate the sum of the first 10. Just take the sum of the first 9 and add 10. So we start to see a different way to define our sum function, which looks like this. Sum of n equals the sum of the first n minus 1 integers plus n. And again, this is for n being bigger than or equal to 1. So, you know, what's the sum of the first 10 integers? I don't know, but if you tell me what the sum of the first 9 is, I'll add 10 to that. And that'll give me the sum of the first 10. So I don't need a loop. All I need to do is have a function that will tell me this value, and then I just do a single addition. One addition, that's it. Now, this formula works great as long as n is bigger than 1. But if I try to use this to find sum of 1, this formula says it's sum of 0 plus 1. And my sum function, I can't tell this function to give me the sum of 0. Sum of the first 0 integers doesn't really make sense. I've said this sum function, we need n to be at least 1. So we can't let this n minus 1 hit 0. So this formula only works if n is bigger than 1. But if n is equal to 1, we already know what sum is. We know that sum of 1 is just equal to 1. So this is a recursive formula. And it's recursive because to evaluate sum of n, we need to evaluate sum of something other than n, some other number, n minus 1 in this case. But that's a perfectly fine thing to do. And logically, mathematically, this works great, right? What's the sum of the first 100 numbers? Well, it's the sum of the first 99 numbers plus 100. The question is, can we use this for something? Can we actually write code that does something based on this to actually calculate the value of, say, our sum function? And the answer is absolutely yes. So let's take the idea of this recursive formula, this recursive definition of sum, and let's turn it into code. So I'm going to write a program called sum.c. And we'll do our usual include in the top. And let's make this function something that takes a command line argument. And if I say sum 5, then this function should print the sum of the first 5 integers. So I'll pass an argc, argv. And if we don't put a command line argument on, so if argc is not 2, so let's see if the user gave us an argument. Alright, so we're going to insist that the person runs this by saying sum followed by a number. And if that number is given, we'll save it as an integer. So let's say integer n, and we'll just say scanf argv bracket 1 %d and address n. Alright, now if the person says sum and they type something other than an integer, then scanf will not return 1, and we could pick that up to say, hey, there's a syntax error. I don't want to get bogged down on that, so I'm just going to assume argument is a legal int. And let's just check and see if this part of our code is working so far. So let's just do a print statement. And let's just print out the value of n and make sure everything's working here. And I'm going to do something else. I'm going to open up a second window, and I'm going to use this to do my compiling and executing. So I did a %d, there we go. All right, now what I'm doing here is I'm saving myself from having to continually exit VI, right? I've got a second window in the same directory as this one, so I can make my changes, and then I can just Alt-Tab, and I can up arrow and recompile. And if I get an error, I can Alt-Tab, and I can go back to editing inside here, and so on. So let's try sum. If I just say sum, it seems to be sitting here doing nothing. So let's try /sum. So sum is a built-in function, so I probably shouldn't have called this sum. So if I say /sum5, it says argument equals 5. All right, so let me do something else. Let me call this my sum. So here's my sum, and if I say my sum 7, it sees the argument is 7. So that's all just a test to make sure that we can actually grab a command line argument and turn it into a number n. So let's print the sum of the first n integers. So I'm going to call this sum function we haven't written yet, pass it the value of n that we got from the command line, take the return value, print that out. All right, so let's make a function prototype. So integer sum integer. And now let's write our function. So this is going to be int sum. I'll call the argument n. So we're mimicking our recursive function, right? So so what's our basic behavior? Return sum of n minus 1 plus n, right? That's return sum of n minus 1 plus n. That's what our recursive definition of sum is. Just calculate the sum of the first n minus 1 integers and then add n. That's exactly what this line says. But if we allow this call to be made with n equals 1, this will ask for sum of 0. And when sum of 0 is called, this will ask for sum of minus 1. And when we try to find sum of minus 1, this will try to find sum of minus 2. And this will loop forever. And it will never finish. So if we run this, and we ask for my sum 5, it seg faults. Now why is it seg faulting? Let's put in a print statement. And let's see what the value of the argument is inside sum. So I want to put out the value of n. And now let's try my sum 5. And you can see what's happening. It just keeps calling it solved for more and more negative values until it gets down to negative 261,949. But it started off fine. It tried to find sum of 5, which requires sum of 4, 3, 2, 1, 0, -1, -2, and so on. So we can prevent this from misbehaving by using this, what we're going to call a base case. If n is equal to 1, then sum should just return 1. So let me take out this print statement and let me put something else in here. If n equals 1, return 1. So if you're familiar with mathematical induction, the first line is like the base case. It's where the recursion stops, and the second line is like the inductive step, where we move from n-1 to n. So now if I compile this, and I run it on my sum of 5, sum of the first 5 integers is 15. My sum of 3 is 6. My sum of 1 is 1. My sum of 10 is 55. My sum of 100 is 5,050. So look at this program that we've written, right? It's got the boilerplate stuff, the include, the function prototypes, the main program, the parsing of a command line argument, and all of that. But the actual sum function that does the calculation of the sum of the first n integers, it's 2 lines of code. That's it. If n equals 1, sum of the first 1 integers is 1. Otherwise, it's the sum of the first n-1 integers plus n itself. So no looping, no obvious repeated additions, just a single addition. Add n to this number, but the trick, of course, is that this number is being calculated by this function. So what's a little weird about recursion is that this function is calling itself, but that's a perfectly legal thing to do in C and most modern languages. The function can call itself, and it'll keep track of where it is, and if it eventually returns from a call, it will go back to where it was called from and continue. And if you set this up right, you get this nice solution to a recursive function. So that's the kind of thing we're going to be playing with in today's problem set. And recursion is not always the way to solve a problem. Now, a lot of times writing a recursive algorithm is easier than writing a non-recursive one. This may not be the first way we would think of adding the first n integers if someone asked us how to do that. But if we're used to thinking in terms of recursion, and someone says, hey, write me a function or draw me an algorithm for adding the first n whole numbers, this might be something that comes to mind. But that doesn't necessarily make it the best way to do this. And so let me give you one more example of a recursive function that is easiest to write like this, but this is not an efficient way to tackle it. And this is the famous Fibonacci series. And Fibonacci series, if you're not familiar with it, go look it up on Wikipedia. There's a long history of this. It goes back, about 1,000 years. And it's a simple sequence of integers that is just rich with how it relates to our world, the ways it pops up in nature, in music, in art, in architecture. It's something that is sort of fundamental to our existence. And it's one of the simplest things in the world to describe. Just start with a pair of numbers 1 and 1, and add those two numbers together to get 2. Now add 1 and 2 to get 3. Add 2 and 3 to get 5. 3 and 5 is 8. 5 and 8 is 13. 8 and 13 is 21, and so on. So it's a sequence of numbers. It goes on forever. And if we describe this with a function fib of n, the nth Fibonacci number is really just the n minus first number plus the n minus second number. So this is fib 1, 2, 3, 4, 5, 6, 7, 8. If I want to know what the ninth Fibonacci number is, It's just the sum of the 8th and the 7th Fibonacci numbers. 21 plus 13, this would be a 34. All right, so that's how we calculate Fibonacci numbers. But again, we need to have a base case, because if I say what's the first Fibonacci number, it's going to say, well, it's the 0th plus the negative first Fibonacci number. And what's the 0th Fibonacci number? Well, it's the negative first plus the negative second. And we're going to be going down this rabbit hole forever, calculating more and more Fibonacci numbers. We need a way out of this. So we're only going to use this formula if n is bigger than or equal to 3. And we're going to say that Fibonacci n is equal to 1 if n equals 1 or 2. So there's our recursive definition of Fibonacci numbers. And there's our base case, and there's our inductive step. So let's write some code for this. So let's write a function fib.c. So we'll make a function fib, and as usual we'll take a command line argument, and whatever argument the person gives n, we'll go ahead and we'll print out the nth Fibonacci number. So we'll scan in a number, and then we'll print out fib equals, and we'll call our fib function. Right, so all I'm doing is renaming some of these things to use fib instead of sum. But now we're going to do the following. If n is less than 3, return 1. Otherwise, return fib n minus 1 plus fib n minus 2. And there we go. That's our whole Fibonacci function, these two lines. And this corresponds to, if n is less than 3, return a 1. Otherwise, return the sum of the two previous Fibonacci numbers. So if n is less than 3, return 1. Otherwise, do fib n minus 1 plus fib n minus 2. So I've got a typo. I forgot my semicolon. And so let's say fib 3, and fib 3 is equal to 2. Well, 1, 2, 3, that should be the third Fibonacci number. If I say fib 6, that should be equal to 8. Right, so there's the sixth Fibonacci number. 7, 8, we calculated the ninth Fibonacci number. We calculated the 1, 2, 3, 4, 5, 6, 7, 8, ninth Fibonacci number to be 34. Let's see if that works. So fib 9, and that's equal to 34. So these two simple lines of code let us calculate the terms of this series by just using the definition of a Fibonacci number, right? Just take the last two numbers, add them together, that gives us the next number. And we're just using that definition verbatim to create this code. Now we can do this without using recursion. We could write a loop that would start at the beginning and keep track of the last two numbers and keep adding them and so on and so forth. But the definition of a Fibonacci series is, a series of integers where each number is the sum of the two previous, and putting that definition directly into code, extremely easy to do once you're comfortable with this kind of representation. On the other hand, if we wanted to calculate, say, the 100th Fibonacci number, we could say fib 100, and this is not going to come back with an answer. Now, we could do this on paper without too much difficulty. The numbers get pretty big, but we know how to do addition. We've already gone out to the ninth number. The next number is going to be 55, and then 89, and we could just do that, another 90 times, and we'd have our answer. And if we wrote a C program that just kept track of the last two numbers and kept adding them, it would get the answer, you know, in the blink of an eye. But this poor recursive function we've written is never going to finish. It's going to sit here forever and possibly run out of memory, but it's not going to come back with an answer in anyone's lifetime. And so why is this? Well, let's put a little print statement in here, and let's say print let's just print out which Fibonacci value it's calculating each time we call our Fibonacci function. And let's compile this, and let's say fib4. And you can see fib4 is calculating fib3, 2, 1, and 2. And then it finally comes up with an answer. If I call fib5, that's making more calls. If I call fib6, that's making a lot more calls to the fib function. The amount of recursion that's happening is increasing. If I say fib10, let's just put that into word count. We've got 110 calls to the Fibonacci function. If I say fib20, we've got 13,000 calls. And if I say fib30, this will take a little while, we've got 1.6 million calls being made just to calculate the 30th term of this series. So this is not a good way to calculate Fibonacci numbers. It's a really expensive way computationally and memory-wise. And it's a way that in this case would be done more easily with a simple loop. So last thing I want to do is take a look at how we can visualize what's happening when we calculate, say, the 10th Fibonacci number. So if we want to calculate f of 10, that's going to be f of 9 and f of 8 that have to be calculated, right? Because our code says let's calculate f of 9 and f of 8 and then add them together. Well, this first call to calculate f of 9 is going to be another execution of this function, and if we're trying to calculate f of 9, it's going to say, well, I need to calculate f of 8 and f of 7. So this will do f of 8 and f of 7, and f of 8 will require f of 7 and f of 6. This will require f of 6 and f of 5, and you can see what's happening. And down here at the bottom, to calculate f of 3, this will need f of 2 and f of 1. And f of 2 and f of 1, those do not require any recursion. If you try to calculate f of 1 or 2, it's just going to return 1. So these calls return. This f of 2 returns. This f of 3 required recursion. F of 5 required f of 4 and f of 3. And f of 3 is going to require f of 2 and f of 1. And f of 4 up here is going to require f of 3 and f of 2. And f of 3 will require f of 2 and f of 1. And so you can see as we fill in these values, right, we're going to have to do a lot of work to calculate f of 6. All of this work's also going to get done over here. It's also going to get done over here. And it's also going to get done over here. So even for just calculating the 10th Fibonacci number, we're going to have a lot of calls that we have to make to the Fibonacci function. And so this is why the Fibonacci function that we've written recursively is so inefficient, because it's making a lot of function calls, and that all takes time, it takes memory, it takes resources. What we'll be able to do, and we'll go through this closer to the end of the course, is what we call pruning the tree. And we're going to use something called dynamic programming. And the essence of dynamic programming is going to be, hey, if we're going to go through all this work to calculate f of 6, once we've calculated this value, we're going to save it in memory. We're going to make a cache of answers. And the next time we want to calculate f of 6, instead of making all these recursive calls, we're just going to take the value that we saved here and use that. And over here, when we want to find f of 6, we'll use that saved value. and over here we'll use that saved value. And so we will lop off what otherwise would be, you know, this whole structure sitting here, sitting under here, sitting under here. We'll get rid of those. So we prune the tree to make it smaller, and this will end up being extremely efficient in this case. So that's what dynamic programming is going to do for us. That's closer to the end of the course, but that's just something to keep in mind. All right, so the problem sets you're working on today, lots of different examples of recursive functions, and we just want to start getting our feet wet and playing around with this idea of describing a function in terms of itself, right? Something like this, or something like this, right? So we want to get some practice with this, write some code to explore this, and then when we start talking about binary trees, which is coming up soon, we're going to rely heavily on these recursive definitions and recursive functions to manipulate these new data structures we're going to develop. And in that context, it's going to be extremely natural to think about things recursively. And the recursive algorithms we'll come up with will be far easier than the ones we might come up with that don't use recursion. All right, catch you next time.